So then the question is the square of some number 4 mod 5? Is the square of some number 3 mod 11? Those things you can think about in terms of just rote calculation. There are just some things to check. Like if I still have the table up, so like this one, you've got, you got 2 squared is equal to 4. So, that answers this. That says that that's 1. And what, did you figure out 3?
3 over 11. That would be, oh man.
Yeah, these won't help you there. Once you get down to the base of things, this is,
I'm trying to think back to the
these just,
table. That's what I was looking over there.
these just reduce. These just reduce. Once you get down, you want to just reduce them down as far as you can, so it becomes these kind of questions, which we can figure out through base.
No, I was thinking of the tables that were once there.
Oh.
You're good. I think 3 is 1 for mod 11. Ooh, where's that? Was mod 11 the biggest one we got to?
Let's see here. I'll just start thinking through them. So like 3 squared is 9. That doesn't help us.
16 power. No,
6. 6 squared.
Well, that's no fun. I believe in tools. When the machine does it.
Okay. What if you run into something like for mod 11, 3, 5, and 6 are both squares that equal 3 in mod 11?
That's fine. Well, the thing is, you don't have to give all of it. It just, as long as there's 1,
Yeah.
you got it. And there's always a pair. By that earlier theorem, there's always a pair. So, so there's always a pair, right? But it's also kind of sobering because there's just a pair. So when you're looking for, is this number a quadratic residue mod a large prime, there is a 2 over p minus 1 chance that you randomly guess it. This isn't so bad when we're at 5 or 11.
No, that's what I was saying.
Yeah.
I was just like, for relatively small p.
Yeah.
Yeah.
So -1. This one works out to -1.
So you said they proved it in general?
Yeah, the proof is general. Yeah.
That's nasty.
All right, well, he has another, well, if I have time. Let's see if we have time. Yeah, maybe we have time for this. Here's another example.
I'm on full brain power right now.
Full brain power.
Let me just.
You're fine. I'm going to just go over here. Wow, I'm either getting better or lecturing's making me feel better. I don't know which it is. Maybe I should have come to school Monday. Let's see here, example. And I don't know what the cut of his jib is here yet, but I'll show you. 299 over 397. All right. He says, okay, that's 13 times 23. Then what?
That's 1 mod. We can flip it.
Can we flip
We can flip 13.
both of them, can't we?
And then 23 is also 1 mod 4.
Very good. So these are both flip-floppable. 397 over 13, 397 over 23. I'm sure there are people that it bothers them to have me read them that way. There's probably some more proper terminology for that. But anyway, reduce mod 13 reducing mod 13, that turns out to have remainders.
Remainder 7.
Yep, remainder 7.
Good.
Yeah.
The next one would be, come on, think. 400, 3, 25, 2, 4, 6, 8, minus 3. That would be 92, what, remainder? 5?
Almost 6. Close. Okay, so anyway, again, that is 13 over 7 because 13 is congruent to 1 mod 4, right?
So it's 23.
And no, 23 is congruent to minus 1 mod 4.
Yeah.
So that's 2. 2 over 23, 3 over 23, right? Using the multiplicative property once again.
Yeah, okay.
Now,
Rule for 2. 2 is if P is 1, 7, which is not, or no, it's minus 1, sorry.
oh yeah, what's that one that we had to fall back on?
I think it is 7. I think it's P, I think P is 7 mod 8. They're like 2 over 23.
Yeah, 23 is what? It's congruent
I
to,
think it's 7. Because 24 is 4.
oh, mod 8, 23.
Yeah, because that'd be, because 24.
Yeah.
Yeah, because 24 is 0. That means 23 would have to be 7.
Yes. So that's 1, right? Okay, good.
1 there.
So we got,
And then 13, I think.
so he does this one as minus 1 over 7. And 3 over 23. Wait a minute.
Now, where'd you get the minus 1 over 7?
So minus 23 over 3, because these are both congruent to 3 mod. These are both congruent to 3. Minus 1, if you subtract 14 from the top, you get to minus 1.
Okay.
Now that is useful because
Yeah,
we have a rule for minus 1. So if you can convert something to minus 1 upstairs,
Okay, so that means 7 would be congruent.
it's a good thing. What do we got?
3, yeah, it should be 3 mod 4.
So that's minus 1 by the first part of the,
So that leaves us with 23 over 3.
right? Oh yeah, thank you. The minuses cancel, don't they? So 23 over 3, which,
21, 7, so it leaves us with remainder 2.
so is 2 a square mod 3?
No.
Oh, 1 squared is 1,
Just 1, yeah.
and 2 squared is 1. No. So there's just 1. That's still that theorem we wrote at the start of class. It's just that the list of quadratic residues is just 1 long. 1. It comes in a pair, 1 and 1 mod 3.
You could use that right there too,
Mhm.
because it's a 2 over P.
So this is minus 1, which is to say that this is not a residue. 299, what this means is that 299 is not congruent to x squared mod 397 for all x in the integers. You cannot solve that quadratic.
Why can we flip it?
That rule right there, Q over P is equal to P over Q if P is congruent to 1 mod 4, or Q is congruent to 1 mod 4. And, same thing, you just put it a minus.
Okay, so
Yeah, like,
both are equal to 3 mod 4, then it turns to a negative.
yeah, I was just looking for rules we could use.
Okay. And then, so how did you get from 397 over 13 and 397 over 23 to 7 over 13, 6 over 23? That,
So this is the multiplicative rule. 6 is 2 times 3. So 2 times 3.
And then 2 over there, over,
oh no, go from the 397 to the 6 over 23.
yeah, so 2 times, yeah.
Oh, here?
Yes.
Yeah.
Yes.
That's because if you look at 397 divided by 23, the remainder is 6.
Okay.
Like this is congruent to, 6 is congruent to 397.
That's so messed up. So
There's,
it's not a fraction, but then we get down there
It's-
and treat it like that.
well, it's never a fraction. The rule is, though, that you can always reduce the top number, mod the bottom number. Right, because again, the question is, like, the whole symbol, remember what the symbol means? So we've got, x over p, right? This is, well, I shouldn't say x, I should say a over p. This is asking the question, it's essentially tied to the question, is x squared congruent to a mod p have solution,
It's not a fraction, it's kind of just a notation.
So yes gives us 1, no gives us -1. So
But we can reduce the top number by dividing the bottom number in there.
Yes, you reduce it, but you're doing it modulo, you're not doing it in a normal fraction.
So this equation, you can always trade A for anything congruent to A mod P. So for the same logical reason, you can trade A here for anything that's,
3 over 7 is equal to 1 over 7.
yeah. So anyway,
We took a big jump. We were messing with.
yeah,
When we dropped down to 7.
it is,
Whoa, I got lost a little bit.
it's this whole way of thinking and everything,
Oh,
it's
it's
just
perfect.
alien.
It's a little weird, I like it.
You liked it? Yeah.